Hello everybody and welcome to Oceanography 101. This is an introduction to the oceans. Later on this week you'll be getting another presentation from Miss Greco, just getting a little bit more into the nitty-gritty aspects. Today we are going to learn where our water came from. We're going to talk about waves, tides, surface currents, and climate. Ocean zones. We are going to be having a project on ocean zones coming up, a research project. So when we get to ocean zones, I would pay attention to that and kind of get an idea of what you might want to research next week. And the last thing we're going to be talking about today is protecting Earth's oceans. So what is being done and what can we do? Before we begin, I have a warm-up for you. 2 questions. I'm going to give you 1 minute to write your response. So your 2 questions are, what do you think Earth's nickname is? And where do you think our oceans came from? Were they always here? All right, that is time. So we're going to double check your answers. So number 1, Earth's nickname. It is the blue planet. Now I'm going to speed this up. So as you watch our planets rotating here, you notice that most of it is blue. Most of it is our oceans. All right, see, it's nothing but ocean. We're in the Pacific Ocean. Then we're coming across North America, South America, moving on to the Atlantic Ocean. There's Africa. Europe is above that. Moving on to Asia. All right, on to warm-up question number 2, origin of the Earth's oceans. So obviously for this one you did not need to have a correct answer because we still don't really know for sure. However, we do have 2 main theories. Theory number 1, water was already here when the planet formed, but in the form of gases, not liquid water. So as the planet started to cool down, it enclosed itself in rocks that were formed from the liquid lava that was all across our surface. And later, as more volcanoes started to erupt and form, it came out in the form of water vapor. So just as a reminder, I put a little image of an erupting volcano. This large plume that is coming out of the volcano, not only is it filled with rock fragments, but it's also filled with gases, and one of those gases, water vapor. So maybe this water came out in the process of outgassing from these volcanoes. But you think about it and you're like, that must have been a lot of volcanic eruptions. Yes, it was very, very volcanically active way back when, but was that enough? And our second theory is that it came to Earth from space. The reason why we started thinking about this is because if you have a lot of these volcanoes erupting, right, it starts to calm down again, and then there is a period of massive, constant prehistoric bombing of asteroids and meteorites, and even a planet. So during this process, specifically the planet that collided with us, the water that may have formed at this point probably vaporized during the collision. So the planet I'm talking about is a planet called Theia. This is what we think helped to form the moon. Now, Theia collided with Earth, and they kind of like meshed or melted together for a little bit. And then Theia and part of Earth spewed back out into space, and those bits and pieces were circling Earth for quite some time. Some of it did fall back to Earth in the form of your meteorites or asteroids, and the rest of it came together to form the moon. So maybe Theia, that collided with us, might have actually brought a pretty decent amount of water with it. So maybe that is how our oceans got here. Maybe it was a combination of both. Maybe it was something completely different, because we don't actually know for sure. Moving on to the oceans, present-day oceans. We are going to start with waves. What are they? How do they form? So ocean waves, it's the movement of energy through a body of water. Okay, how do they form? Typically by wind or some other disturbance. So wind would provide friction to help, quote-unquote, move the wave. And the major disturbance that could take place that would form a wave is an earthquake or a landslide. Now, just as a quick demonstration, if you have long sleeves on, stick out one of your arms. I'm going to use my left arm, and I'm going to put my right hand on my left wrist. Now, I want you to move your hand up your arm and watch what your sleeve does. Creates a little wave, right? Kind of crinkles your sleeve. So, kind of similar to what the wind does to the water. The wind provides that friction and helps create that movement of energy, right? For bigger waves, you need higher wind speeds. You need the winds to blow for long periods of time and or longer distances. Or your major disturbances, your earthquakes, your landslides, those are going to give you your much bigger waves, especially if you have an earthquake in or near the ocean, you get something called a tsunami. So how do waves actually work? Remember that example I just had you do with your sleeve, where you moved your hand up your sleeve and it kind of crinkled your sleeve? That is an example of the common misconception. So the misconception or the lie, maybe not lie is the best word, but not the truth, we'll say, is that waves move the water. So when you did that example with your sleeve moved up your arm. But the truth is that it's the energy that's moving through the water. The water actually stays where it is, even though it looks like it's moving. Okay? So, really weird to imagine energy and what that looks like. So I found a nice little video demonstration here for you. Alright, so this experiment, they are using a water tank, just a rectangular tank filled with water, and they are making waves. So they're going to put a ball on top of the water. You can see it just kind of bobbing up and down or like in a little circular pattern, but it doesn't move down the tank. So if we take a look at what would be the molecules within the water, you can see here it does look like it's moving down. But if you focus on just one of those molecules, It's actually just going up and down in place. That red dot is not actually moving down the line. Same as what you're seeing with the ball floating on the water here. The energy is being transferred. The water itself stays exactly where it is. It just moves up and down a little bit. All right, so waves near shore. Now we're going to move on to what happens to the energy, the molecules, basically the wave itself as you move from the deeper parts of the water into the shoreline. So in the deep water, you have longer waves, and they're a little bit lower. They're more stretched out here. As you move closer to the shoreline, the waves tend to slow down a little bit and scrunch up, and they get a little bit taller too as they get closer to the shoreline. So we're going to focus over here first in the deep water. You notice under all of the waves, there's these little circular patterns. These little circles represent the molecules within the water and the energy transfer. So remember, waves are created because the energy in the wind transfers to the energy in the water. And that energy is moving through the water with the wind, but the water itself is staying still. So these little circles represent the molecules moving. Now, as you get further down into the ocean, you notice the circles get smaller and smaller. It's because the impact of the wind gets smaller and smaller the further down you get. Once you get to a certain point in the ocean, you can't even feel the waves anymore. But as you get closer to the shoreline, the bottom of the waves and those molecules actually start to drag a little bit. So there's a little bit of friction created on the bottom of the seafloor. So the bottom starts to drag while the top still wants to move a little bit. And after the top of the wave reaches a certain point, it starts to kind of bend back towards the sea, and you get this nice little ocean wave shape. Like if you've ever drawn the ocean, this is probably close to the shape you're giving it. And once it reaches a certain point, it breaks. That's where you get this white foam. So all of that energy is released and it surges up onto the shoreline. And then gravity pulls that water back into the ocean. And you get this constant flowing of energy up on the shore and pulling it back into the ocean. And that's what you're observing if you stand on the coastline, or if you're at the beach and you're watching the waves crash on shore. That's what's happening. And that's why you don't really see as much of the wave breaking or waves breaking out in the deeper water, because you don't have that friction. One other thing to mention here is that the sea floor does play a pretty decent role in what the ocean does and what it looks like. So on the East Coast, we have a nice gradually sloping shoreline, and the wind is actually pushing away from the ocean for the most part, away from the shoreline for the most part, going out towards the ocean. And over on the west coast of the United States, we have a pretty steep shoreline, or steep continental shelf and slope. So it's not this nice gradual moving onto land. It's like up cliff, here we are. And on top of that, you have the wind also bringing a lot of that energy towards the shoreline. So we have much bigger waves out on the west coast than we do on the east coast. So your wind obviously plays an effect here, as well as the shape of the sea floor. So if you ever are interested in surfing, head out to the west coast. You probably catch some bigger waves out there. On to tides. So this is going to start to get into like the actual movement of water here. Tides are the daily rise and fall of Earth's waters on its coastlines. And always has to do with the interaction between the sun, moon, and the Earth, nothing else. That interaction that we're talking about is something called gravity that helps you and I stay grounded on our planet. But it is the force exerted by an object that pulls other objects towards it. So we'll get more into gravity and tides when we get into astronomy. But I do want to share part of this video anyways with you, because he helps to demonstrate both of these images and kind of get a better understanding of gravity and the interaction between these. So watch about a minute of it.
Hey, check. Big deal to it. Imagine for our purposes the Earth is right here and the Moon is directly above it. Now, they exert a gravitational pull on one another, and since on the Earth most things are pinned down, we have shoes, buildings have foundations, stuff stays in place. But the oceans, being literally fluid, actually can be pulled toward the Moon, and this is what creates the tide. The Moon's here, it's pulling on the ocean at the top of the Earth, creating a high tide on the top. Now on the bottom, another high tide is created because the Earth itself is pulled toward the Moon, even though the oceans down here have less gravitational pull exerted on them, being farthest away from the Moon. So on the top and bottom, you have high tide because of the tidal bulges, and on the sides that are at right angles to the Moon, you have low tide because the ocean's stretched thin over the surface of the Earth. Pretty crazy, huh? So, like I said, the sun also exerts an influence on the tides, but it's less pronounced than the moon's. See, it actually enhances or diminishes the gravitational pull of the Moon here on Earth. When the sun and the moon are in alignment, the sun enhances the moon's gravitational pull, creating higher tides than normal. They're called spring tides, and they happen on a full moon or a new moon. Now, when the sun and the moon are at right angles to one another, with the Earth right about here, the sun diminishes the gravitational pull of the Moon on Earth, creating lower than normal high tides, also called neap tides. These happen on the quarter moons because the Earth...
All right, so like I said, we'll be learning about this a little bit more later on. And in astronomy, it'll probably make a little bit more sense than what it does right now. But tides do help to physically move the water. Waves, not so much. Surface currents, going back to these, specifically, like, what are they? In general, these carry warm water from the equatorial regions up to the polar regions, and then your cold water gets carried back down to the equator. So you bring warm water from the equator up to the poles, and your cold water from the poles back down towards the equator. Simple as that, except it's a little bit more complicated. And as mentioned at the beginning, we are going to talk a little bit about climate here. So these surface currents do impact coastal climates. So your warm water currents hold more moisture in the air, which gives you a more mild, wet climate. You're more likely to experience precipitation and pretty decent amounts of it. Your cold water currents hold less moisture in the air and help to create a more dry and sunny climate. So the current that helps to influence the east coast of the United States is called the Gulf Stream. It moves from the tropics down here all throughout the Gulf of Mexico, wraps around Florida and up the east coast of the United States and out into the middle of the Atlantic Ocean, and eventually will make its way back down the west coast of Europe and Africa. If you're looking at a thermal image or looking at temperature of the water, you can actually see the heat transfer. All this really dark red is your really warm ocean surface temperatures. And that dark red and your reddish orange does transfer up the east coast of the United States and eventually makes its way out into the Atlantic Ocean. Now, all of your bluer colors, this is your colder temperature, and we are right up here. So we have a good mix of cold water and your moderate water temperature, so not hot, not cold. But as you move further south on the East Coast, you really get that influence of the Gulf Stream, which also kind of helps to influence the amount of tropical storms and hurricanes that we get in this area. They love warm water and moist air. If you look over on the west coast of the United States, it's Alaska right up here, and Washington, Oregon, and California, Mexico down here. You can see that there's some warm ocean water. There's Hawaii right here. And there's really cold ocean water up near Alaska. So there's two different currents that take place here, with one moving down towards Mexico and one moving up towards Alaska. But as you can see with the thermal imaging here, that warm water doesn't really reach the west coast of the United States all that well. You actually get more of that cold water from the polar regions transferring down the west coast, which is why you see more of your drier climates here. In the summer in California, it is very, very rare to see precipitation. I went out to visit my cousins, I don't know, probably like 6 years ago now, and we were there for a week and a half in July. It did not rain once. Barely any clouds. It was hot and sunny, but it was weird because on the East Coast here, we get hot temperatures. It's always really humid and sticky. It's just miserable outside. And then when I was visiting my cousins in California, it was like 104 degrees, but not nearly as bad as if it would have been 104 degrees here, because they don't have that moisture in the air making it sticky. On to ocean zones. So there's a few worth mentioning here. One being the Nordic zone. Now, the Nordic zone is what extends from the low tide line, or basically your shoreline, out to the edge of the continental shelf. So right here you get a lot of sunlight. There's a ton of nutrients that are being washed from the shore into the oceans, which means that you have a lot of creatures living here. A lot of sunlight, lots of nutrients. You have lots of creatures, both plants and animals. In the base of the food web here, we have something called plankton. All right? You guys were probably thinking of this guy, plankton. But he's the base of the food web in the Nordic zone. This is like where the most energy dense food is. And every other creature that lives here basically has plankton to thank for that. Now the Nordic zone I have divided into cold and warm. So the cold Nordic zone, or cold Nordic water, could be home to something called the kelp forest. So in order to have a kelp forest, so this is typically like western United States, like northern California area, but you need a rocky bottom to anchor the kelp to. And they can get up to almost 100 feet tall. So they're actually kind of heavy. But what helps to keep them afloat, they have these little gas bulbs on here that kind of act like balloons that, keep them upright in the water. This is a major habitat for young creatures like gray whales trying to escape prey. There's little slugs and snails that live on the holdfasts, or the roots that are anchoring to the bottom. And one of my favorite animals, the sea otters, they feed on sea urchins that actually eat the kelp. So if we're doing things right, we should have this equilibrium here, where the sea urchins get to eat the kelp, but not too much, The sea otters get to eat the sea urchins, but not too much there. However, what we have seen is that with sea otters disappearing from these locations, the kelp has also disappeared. Back in the day, people used to hunt sea otters for the fur. They are significantly more protected now, but because of the sea otters not living in these locations, you have a lot more of these sea urchins taking over and eating the kelp. So kelp forest is kind of in danger here. And just a few more sea otter appreciation pictures. There they are eating the sea urchins. Fun fact about the sea urchins, if you ever step on them, good luck. Because each one of these little spikes, it's actually more like a pack of Smarties, if you've ever had that candy, where it's not a solid spike, it actually breaks off, kind of like your spine. There's like different pieces within there. So, very painful if you ever step on that. And again, just some more appreciation because I think they're adorable. Now, your warm Nordic zone hosts your coral reefs. So this is in shallow tropical ocean water. I want to say only, but you can have a coral reef elsewhere. But typically in your shallow tropical ocean water. And coral are actually pretty cool because you would think that they're just like these rock-looking things, but they're actually animals. Colonies of animals that are about the size of a pencil eraser. So the coral animal itself produces a hard outer shell, and as they die, more grow on top, and they kind of attach themselves to each other. So the coral reefs that we see today have been growing for about 5,000 to 10,000 years. However, with ocean acidification, basically like the ocean warming, the microscopic algae that live on these coral and help provide food for them, it's like a symbiotic relationship, right? They need each other and benefit each other. So with the ocean acidification, there's something called coral bleaching, where these microscopic algae leave the coral because they can't handle the ocean water anymore. They become stressed, they leave. And that's where the corals get their color from. So you're just left with the shell, which makes it look really white and dead. So real quick before I show you images of coral bleaching here, it's an up close of one type of coral. You can see there's like little creatures here. Now they kind of look like animals, and I almost said, sorry, kind of look like plants, and I almost said plants, but they're actually animals. So they use plants for food, but they are considered an animal. And the coral reef itself is home to so many different species. It's been compared to the rainforest on land. The rainforest has the most diverse plant and animal, I almost want to say collection there, but habitat on land, and the coral reef has the most diverse habitat or ecosystem in the ocean. But with ocean acidification, a lot of the creatures that live here have either died off or left because they use the coral for protection, for food, for shelter. All right, so you have your healthy coral that has all of your microscopic algae living on the outside of your coral. It's little dots in here, providing food and energy for the coral. The bleached coral, like when it can't handle the ocean water anymore, that algae leaves. It gets stressed. It can't handle the situation anymore. So the color disappears and you get this kind of like bone-like structure. And then you get something called turfing algae on there, which is just a pure sign that it is a goner. So if your coral is bleached, it doesn't necessarily mean that it's dead. But if you see this kind of like foamy appearance to it, that's when you know the coral has completely died off. There's another image here, healthy coral, and then one that has passed on. Now we're going to take a look at the open ocean. So this is, the open ocean itself is huge. It extends from the continental slope all the way out to the next continental slope. But it extends, sorry, if we're talking about the surface, it extends as far down as the sunlight reaches, which is about 650 feet. In this area of the ocean, there's not as many nutrients. You don't have that washing in from the shore. But you still have the growth of algae here, which is the base for the open ocean food chain. So you still have creatures that live here, and they still have an abundance of nutrients, just not as much as your Nordic zone. One thing absolutely worth mentioning about the open ocean surface zone is our little friend called the blue whale. And by little, I mean huge. So an adult blue whale is about the length of 3 school buses, right? Huge. It is the biggest animal that we have ever had on our planet. There's a few theories as to why, but I'm not going to get into those just yet. And a comparison between a blue whale and a human. Right, imagine being out on a boat and these guys coming up. So the fishermen are fishing, and so are the whales. One fun fact before we move on. A blue whale's tongue weighs the same as an elephant. Just for size perspective here, these things are absolutely massive, glorious creatures. But on to the deep ocean. I think you might be a little bit more interested in this once you get to see some images. But it's much, much darker, to the point where there's absolutely no sunlight. It is pitch black. So it gets darker and colder the further down you go. And it's pretty desert-like. There's not very many organisms. So the ones that do live here have some pretty crazy adaptations. One of them being something called bioluminescence, which is the production of light by living things through different chemical reactions. If you've ever seen fireflies or the little bugs that blink like a yellowish green in the summer, it's the same thing. But the fish in the ocean, or the creatures in the ocean that produce this bioluminescence, either have light-producing organs, or they have bioluminescent bacteria living on them. So as mentioned, food supply is limited. It's kind of desert-like. So these weird adaptations, including bioluminescence, help to make them some pretty excellent hunters. Another reference to Finding Nemo here, one of my favorite movies. The anglerfish in Finding Nemo. If you have never seen this movie, I highly recommend it. But here's a little example of bioluminescence right there. He's using that as a fishing lure to lure his prey in. This is what the fish actually looks like. And another fun fact here, the female is always the one that looks like this. It's bigger, it's more aggressive, and the male is really, really, really tiny. So when they're ready to mate, the male attaches itself onto the fish and gives it the sperm so it can reproduce, and it basically just acts as a parasite to the female for the rest of its life. It permanently attaches itself to the female. And she is the one doing all of the work with this glorious face of hers. Google anglerfish if you want to see more pictures like this. They also have this bioluminescence as a sort of defense. So if a predator is coming towards, let's say, this little shrimp here, the shrimp sprays or squirts out this bioluminescent stuff in the predator's face, and it can run away, hopefully safely. And we have an image of a jellyfish over here creating some bioluminescence. And you have some fish that have pretty much like see-through parts of their body. This could be for camouflage purposes. You can't physically see it. Or it could be hunting purposes, like, again, camouflage, but maybe you have more peripheral vision or more access to seeing what's around you if you don't have like skin or bone blocking it. This is a squid in the deep ocean. So if you were to go down in a submarine, you might see something similar to this. And another creepy little dude here. Weird face. The eyes on these are always big. Nocturnal animals have huge eyes. Helps them see in the dark a little bit better. There's another fish. I don't remember the name of this one. But if you've noticed, all of these predators have really big teeth that are kind of angled inwards a little bit. It creates a trap or a cage. So if they do actually catch something, the prey can't get away. It's your goblin shark. All right. Kind of reminds me of like a character from Harry Potter, maybe. You have this weird little nose-looking thing, and these little scrawny, jagged teeth. And you can see in here specifically, the teeth are angled inwards. So if it catches something and that fish tries to leave, it's getting stuck on more teeth. So these are some of the adaptations that were made. And this last image, hopefully you'll get a nice laugh. This is called the blob fish. Look at him. This is a real thing. That's all I'm going to say. Moving on to hydrothermal vents. These are found near mid-ocean ridges. And what happens here at mid-ocean ridges, these hydrothermal vents, there's really, really cold, almost freezing water that's really highly pressurized, and it seeps into the cracks near the mid-ocean ridge, comes in contact with your molten magma or your rock, and because the magma is already so hot, the temperature of that water instantly skyrockets up to like 750 degrees Fahrenheit or more, and then it shoots back out through these hydrothermal vents in the form of a plume that's made out of highly mineralized material. So really, really hot water that's coming out of here, even though the ocean water nearby is pretty close to freezing. So this is some really intense living environments, even though we still have creatures here. There are plants that live down here, and they use something called chemosynthesis for energy, which uses heat and chemicals to produce food. And because we see plants there, we also see some animals. Before we get to the animals, though, just some images of your hydrothermal vents. You may remember from plate tectonics, right? These are also called black smokers, by the way. You might remember that term. These little red and white things are called tube worms. We have all sorts of creatures that live down here. There's little fish, octopus, starfish, shrimp. I believe there's even some corals that live down here. But this is where we think life on Earth may have once started, at an environment similar to this. The last thing worth mentioning today before we leave is just protecting Earth's oceans. We have learned about possibly how they got here. We've learned about waves, currents, tides, and zones within the ocean or different ecosystems. So now for protecting and maintaining the oceans. First question is, who actually owns the ocean? That's been a very big debate in the past, and the United Nations established boundaries here. So each nation or each country controls about 22 kilometers out from its coastline, which is, I believe that's the blue here. Oh no, that's the continental shelf. Sorry. But the resources on the continental shelf extend out to about 370 kilometers of their shoreline, which is the blue surrounding each one of these. Resources, that's like your ores, your gas, your oil, even treasure sometimes. And then everything else is called high waters or high seas, which is where it gets kind of tricky. Now, the most important thing here is the pollution that we see. And this has been an international effort. So every single nation, pretty much every single nation, has made some sort of efforts to maintaining the oceans and cleaning it up. And some of these include marine refuges, building more eco-friendly boats and tankers, monitoring runoff. Remember last week and the week before we were talking about surface water. So when you have contaminated surface water or polluted surface water running into the ocean, that causes some big problems, specifically for the ecosystems along the shoreline. And garbage dump monitoring, we don't want to add to the garbage patches, and different cleanup events as well, which could mean like oil spills or garbage or anything in between. So a few images to leave you with today, just to help kind of solidify your understanding of the importance of taking care of our oceans. All right, so that is the end of Oceanography 101. Throughout this week, you will continue to expand on what you have learned today, and I look forward to seeing your projects coming next week. If you have any questions, don't hesitate to ask your teachers. If you missed any of the questions throughout, just make sure you go back and take a look at them. And hope you have a great rest of your day.